I'm gonna talk about future location benchmark with ArgoUML SPL. First of all, it is important to know what is future location. And for that, let's suppose that we have a software project that I'm gonna call BWin, and it's conformed by some software feature. For this example are F1, F2, and F3. Each of those are made of different implementation elements that could be classes, methods, variables, and so on. What is future location? Identify and establish the mapping between each feature and the orientation elements. So let's go with a future location case in families of systems. That is an usual case because it's normal to have a family of systems that have been built through clone and own or copy paste modify techniques, and normally this is the beginning of the adopt of an SPL of software product line. For that, it is important to identify what are the usable assets of the SPL to reuse it in an efficiently way for new systems. All of these are mainly used for extractive approach to build reusable assets. It is important to mention that there are a large amount of different techniques to implement this future location, and there are a lot of different research and it's hard to determine what is the best technique. What is ArgoUML SPL? There are some cases that are used to test future location techniques, and one of those is ArgoUML, and I'm gonna say that is the most important because it's the most used case for testing future location, as you can see in the table. First, I'm gonna show you some of the features that has this test case, and that would be that this case has 256 possible variants, and each of those has a mean size of 110 kilogs and also a max size of 148 kilogs. The way that code under team do it was through Java annotations on the source code. They define and comment with if notation, and they determine what is the feature that they're gonna implement. So through Java annotations, they set what part of the code is related with each feature. And with all of that, why a benchmark about ArgoUML? And the elements related with this, it's related with 3 different problems, and our future location tried to solve that main problems. That would be that there are different variants, there are different granularity level, and there are no unifying metrics. And that is equal to have a great case study but non-unified. And for that, our future location proposed a predefined scenarios, a ground truth established to compare them between them, and a group of defined metrics. Let's go for the first one. The predefined scenarios that we propose are the original one, that is one variant with all the features present. The second one is the traditional, that is the most repeated case that is used in the literature. I'm gonna set that there are 10 set of variants. Also, there are pairwise interaction that are the configurations that were used using T-wise algorithm. Also, we have the randomly scenario, and it is important because it consists of generate 11 scenarios of X variants, and it helps to show how sensible the technique is regarding to the number of variants. And finally, a scenario with all the variants. And this scenario is important because it helps to show the scalability of the technique. Also, it is important to say that all these predefined scenarios are generated without the variability related source code comments, and that means the Java annotations that code to use to create the SPL at first. In other words, as an example, as you can see, the orange square shows variability related comments that could be used to know what are the features that are related with each part of code. And in the other hand, we have the green square that show normal source code comments that are not directly related with the variability family. There are normal comments that doesn't affect the family system. In second hand, we have different granularity level, and for that we establish a ground truth. And to explain the ground truth, it is important to show how implemented elements look in our benchmark. In this example, we have parts of code that are inside of the cognitive comment, but as you can see, the entire class is inside these comments. So for explain how this class is related with this feature, we have to write it in right way. That would be a class related variability trace. On the other hand, we have a segment of code that it's not actually the entire class, it's more a part of the code. That would be a class but with a refinement tag, because as I said, it's not the entire class. That would be just a segment of the code, and for that we have to write the name of the class, all the paths, with a refinement tag, because as I said, it's not the entire class affected. But also we have these methods. As you can see, we have the function log version info that it is only present with the login feature. But what happened if not the function, instead part of the function is affected with when a feature is present? So easily we just gonna set that we just mention the function with a refinement tag as the example class. We have, as you can see, a big amount of class qualified name, methods, also class with refinement tags and methods with refinement tags. For our challenge, the expected format for our for us is mentioned for each feature, or for each feature interaction, the class that have to be or has to be present in the file. So for example, that would be the class, or the class with the refinement tag, or the methods, and so on. We have txt files for features, feature negations, pairwise interactions, and treewise feature interactions. And all of those you can you can find it in the GitHub project. Finally, we have the non-unified metrics problem, and for that, we just plot automatically your results with a precision and recall and F-score metrics, and that are automatically calculated by our in our project. And that's all. Thanks.